Okay, let's get started. How's everyone doing? Maybe we'll do like a sort of mid-semester, or I guess we're almost like a third of the way through, I guess. I don't know, 1 month in. How are we doing? Show of hands, who's like, we're gonna do like on a scale from 1 to 5. Who's a 5 right now with this course? Who feels pretty confident with this course? Nobody? Okay. Who's about a 4? 3, 2, 1, off the chart, 0. Okay. So that's sort of about what we expect. It's about a 4. 3, 4, you're at that spot, you're probably good. Just, keep working on it. All right, so last week, I think I ended off talking about the inverse of a 2x2 matrix, right? So we had a formula for it. I believe it was 1 over AD minus BC times DA minus B minus C, like that. That was the inverse of our 2x2 matrix. And I think maybe a natural question is, how do we find the inverse of like a 3x3, right? Another sort of very natural question is like, so if we look at this bit at the bottom there, that AD minus BC, we said the inverse only exists if that number is not 0, right? If it's 0, you can't divide by 0, so the inverse doesn't exist, right? So that was one of our like sort of criteria to see if a matrix was invertible or not. So again, a natural question is there a similar thing we can do for like, 3x3 or n by n, right? However big we want to get. So turns out there is, and we're going to talk about that. So first off, I just got in case anyone's wondering why I'm on my phone, I forgot my notes. So I'm just like reading off examples off my phone. Hope that's good. So say that we want to find the inverse of the matrix 3, 0, 2, 2, 0, minus 2, 0, 1, 1. What we'll do is we'll write out the matrix, and then we'll write a vertical line, and then we'll put I. So identity, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. Like that. So this is like, the way we might say this is that we have A augmented with I. And remember, this line, it's sort of the same idea as like the line when we were doing like solving systems, right? And you were using Gaussian elimination. It's the same sort of idea here. It's just the only difference is that there's 3 things after the line instead of 1. It doesn't make any difference. And again, the line doesn't have any like bearing on the math that you're doing. It's just like a reminder that there's like something different going on here, right? So what we do then is we just row reduce. How should I row reduce this? What's a good first step? Any ideas? Yep. Switch the 3rd row with the 1st row. Why are we doing that?
Oh, wait. Do the 1st row minus the 2nd.
Yeah, that's what I would do. I would do row 1 gets row 1 minus row 2. Because then we'll do 3 minus 2, that'll get us a 1, right? Which is kind of, we want leading ones, right? So we're row reducing, just a normal Gaussian elimination, except we have more numbers, right? So we're doing row 1 gets row 2, sorry, row 1 minus row 2. So we're doing this minus this. 0 minus 0 is 0. Positive 2 minus negative 2 is positive 4. 1 minus 0 is 1. 0 minus 1 is minus 1. 0 minus 0 is 0. And then everything else stays exactly the same. Like that. That's a good first step. Next step, any idea what we should do? Any suggestions yet? Switch row 3 and row 2. Yeah, sure. Row 3, switch with row 2. What we'll end up getting is 1, 0, 4, 1, minus 1, 0, 0, 1, 1, 0, 0, 1, 2, 0, minus 2, 0, 1, 0. Like that. What now? Starting to see that like leading one staircase sort of pattern coming in, right? Good. Yeah, get rid of that too, right? So we'll do row 3 gets row 3 minus 2 row 1. Does that seem right to get rid of that too? So first row stays the same. Second row. And third row, we're doing this minus 2 of those. So 2 minus 2 times 2 is 0. 0 minus 2 times 0 is 0. And we've got minus 2 minus 8 more, so it should be minus 10. If I make a math error, let me know. 0 minus 1 is negative 1. 1 minus negative 1 is positive 2, and 0 minus 0 is 0. Hopefully I did that right. Did I? I think I made a mistake here and here. 0 minus 2 times negative 2, or times negative 1 is negative 2. And 1 minus or plus 2 should be 3. Did I make any mistakes? It's possible. Looks good to people? Cool. Okay. So, sort of next step, maybe I'll do row 3 gets row 3 divided by negative 10. Seems pretty good. Gonna have to go to fractions, but that's okay. 0, 0, 1, 0, 0, 1. This will be I guess 2 over 10 if you want to write it like that, 3 over 10 and 0, or this should be minus 3 over 10, I think. Like that. Cool. So now we're in REF, but let's keep going and get into reduced row echelon form. For the inverse problems, you always want to go to reduced row echelon form, go all the way to reduced, and you'll see why. So to get down to reduced, maybe I'll do row 2 gets row 2 minus row 3. So that'll get rid of this one here. I'll be left with first row stays the same. Second row, we're changing, so it's going to be this minus this. So 1 minus 0, well, 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus 2 over 10 is negative 2 over 10. 0 minus negative 3 over 10 is positive 3 over 10. And then 1. And then last row stays the same, I think. 0, 0, 1. 2 over 10. Negative 3 over 10, 0. Think like that. Now what we have to get rid of is that 4, right? So maybe I'll just do it up here because I'm running out of room. So the next step is going to be, we'll get row, well, we'll do row 1 gets row 1 minus 4 row 3. I think that should get rid of this 4. Good with that. So I'll end up getting, for row 1, we're doing this minus 4 of these. So 1 minus 4 of 0, 0 minus 0, 4 minus 4 of 1 is 0, 1 minus, so 4 times 2 over 10 is 8 over 10. So we're doing 1 minus 8 over 10, which is 2 over 10. This one, it's negative 1, So we're doing -1 minus 4 times 3 is 12 over 10. But it should be minus and minus makes plus. So that is 2 over 10. And then 0 minus 0 is 0. Does that look good? Cool. And then the rest of it all stays the same. Sorry, minus 2 over 10, 3 over 10, 1. Like that. Good with that? So now we've reduced it all the way to RREF because we have leading ones, everything above and below it is zeros. In the staircase pattern, right? There's no rows of zeros, so it doesn't really matter about that point. Once you have it into RREF, the sort of magic trick is that what you have left is I with A inverse. So this bit here is A inverse. Just pops out kind of weird, right? So any questions about inverses of matrices? You can do this with any size now, right? How would you know if it's not invertible if you went through this procedure? Yeah.
You got a row of zeros?
Exactly, right? If you have like a row of zeros, if it's not like the identity on this side, then yeah, exactly. All right. Now there's another way to tell if a matrix is invertible or if it's singular, which is the opposite of invertible. Anyone know what it is? Yeah.
It's if the determinant does not.
Yeah, so if the determinant is not 0, then it's invertible. If the determinant is 0, then it's singular. It's kind of backwards-ish to what you'd think. But yeah, like it's that whole idea of like dividing by 0, right? So if it's 0, that's bad. You can't have an inverse sort of idea. What is a determinant? So the determinant, I'm not gonna there is a geometric explanation for what the determinant is, like a visual thing. I'm gonna show it to you next week because I wanna give you a bit more time to settle into determinants before I show you what it means. I know that maybe seems a little mean, but my hope is that you can understand the calculations and not get confused by the visualization, because the visualization is kind of confusing. That's why I'm holding off, but I will show you that next week. It's a weird idea, but yeah, so another thing about determinants is there's sort of 2 schools of thought in linear algebra, specifically people who teach linear algebra. The first school of thought is that determinants are great and they're great for calculations and they show you if things are invertible and stuff, right? Among other things, right? Like I think you've touched on Kramer's rule already in lectures. Have you? Or maybe you're touching on it today or tomorrow. It seems right. You'll learn about a way to use determinants to solve a system instead of having to do Gaussian elimination, almost a shortcut in a way. So it's kind of nice in a lot of ways. That's one school of thought when we're teaching linear algebra. That's the way that this course goes. The other school of thought is that determinants suck because they're hard to understand, which they kind of are. They're just do this weird, cryptic zigzag pattern, and they're just annoying sometimes. They're really easy for computers, which is why we teach it to you this way, because a lot of you are computer scientists and you probably want to know how the computer would do it, right? They're very hard for humans to calculate a determinant. It's not easy. So yeah, that's, and if you ever go on to study further linear algebra, some of the 2 main books that are used to teach it are Linear Algebra Done Right, which uses no determinants, and Linear Algebra Done Wrong, which uses determinants. It's a big feud going on in math. It's been going on for years now. we're using the sort of done wrong approach and teaching you determinants. So yeah, if you hate determinants, you can study on your own how to not use determinants. It depends on the case, but there are ways. So let's talk about determinants. So if I have a 2x2 matrix, A, B, C, D, we already know what the determinant of that is, right? Anyone remember? Yeah. AD minus BC. Right, so you do everything across this way minus everything on the other diagonal, if that sort of makes sense. So it's AD minus BC. It's kind of weird. Again, why are we doing it this way? I don't know. Well, I do, but you know, it's hard to explain, right? Yeah. So as an example, if we did like 1, 3, 4 minus 2, and took the determinant of it. Also notice for determinants, we use straight brackets, right? Yeah. The determinant of this matrix, we're going to do 1 times -2 is -2, and then minus whatever's on the other side. So 3 times 4 is 12. The determinant is minus 14. And since that determinant's not 0, this matrix is invertible, right? If it is 0, then we couldn't do the inverse. Does that make sense? All right. Let's talk about 3x3. Let's say that I want to find, maybe I'll find the determinant of this matrix that we started with earlier. So say I want to find the determinant of this matrix. There's a bunch of ways to do it. And this only works for 3x3. So what I'm about to show you, don't try and do this with a 4x4. It's not going to work. First step is write down the matrix, everything inside the matrix, again, just below it. So 3, 0, 2, 2, 0, minus 2, 0, 0, plus 0, 1, 1. Like that. That's the first step. Next step, if you have multiple colors, great, because it's easier to see that way. Draw lines going through like the main diagonal direction, connecting 3 numbers together. So, and then move your way down. So like this, this. And you're drawing 3 of them. Why 3? Because it's a 3x3 matrix. I don't know, there's not a good explanation. If that helps you remember 3, great. Then get your other color, if you have it, and draw the other diagonals. Like that. See that? Yep. Yeah, same thing. Whatever you prefer. Because like really, in this case, we don't need this because we're not using it. I just wrote it because, I don't know, out of habit, I guess. But yeah, whatever way works for you, it doesn't really matter. I'm just showing you the way that I usually do it. You eventually can just do this in your head. There's a bit of a shortcut to it, but I don't know. It's hard to explain it, and if you don't see it, you're gonna struggle with the explanation of like the shortcut. So we'll just do this way. So what you do is you multiply along those green arrows that I drew. So you're doing 3 times 0 times 1 is 0. 2 times 1 times 2 is 2. Adding them together. And then 0 times -2 is 0. And then you're subtracting the red ones. So 2 times 0 is -0. -2 times 1 times 3 is -6. We're subtracting -6, so it's +6. And then 1, 0, 2, 1 times 0 times 2 is 0. So the determinant of this matrix is 2 plus 6, which is 8. Yep.
For
outputs.
Or am I doing this wrong?
No, you're right. Yeah, I don't know, did a math error. So it should be 10. Thanks. Yeah, it's 2 times 1 times 2 is 4. This is why you take it slow, because on a test, it's super easy to do something like that, or, you know, sometimes people will do like say I was going across this diagonal here, this minus 2, 1, 3. A lot of people will do like minus 2 plus 1 is -1 plus 3, and now you're all screwed up, right? They'll add instead of multiplying or something, or I don't know. So yeah, be careful. Awesome. So so that's how you do a 3x3. If you want to see the weird 3x3 trick, I'll show you it. It's sort of the same thing. It's just lets you do it without writing a bunch of stuff. So the way a determinant works mathematically is that we're picking, in a sense, we're picking like, it's almost like Sudoku. So we're like picking one thing from each column and each row and multiplying them together. So if you don't get this, just tune out, I don't care. What I do, if you're doing it quickly, is you multiply along this green line here. Then you draw like the 2 lines that are next to it, sort of parallel. Now we need to get something from every row and every column. So like, say we consider these 2, we need to pick a third element. It's either going to be this one or this one, because those are the only 2 that are left over. But if we're doing these 2, then like this one's already in this row or this column, for example. This one is in like a different row and a different column than all the others. So you like multiply those 3 together. And you do the same thing here. And then you do the same things for the negatives. It's a little bit of a shortcut if you can see like the weird pattern. If you can't, don't worry about it. If you want to talk about it, talk about it after class or office hours. Any questions about that? All good? Cool. Okay, so let's talk about determinants in general. So I've showed you how to do a 2x2 and a 3x3. How do we do a determinant sort of in a general case? One method to doing it, there's a couple, and I think you learned one this week already. One of them is called cofactor expansion. Cofactor expansion it's kind of a pain, but it's how I think it's how computers do it. There's probably optimizations that computers use now, but it's probably what the original computers used. So say that I want to find the determinant of, I guess I should do this, determinant of the matrix 7, 2, 1, 0, 3, 1, -1, sorry, -3, 4, -2. Now I could do the 3x3 trick here, but let's pretend that we don't know the 3x3 trick, right? Because this method will work if it's a 4x4 or a 5x5, right? So what we do is pick a row or a column. It can be either, whichever you prefer. You pick any row or any column on that matrix. The idea, if you're like trying to be strategic about it and like pick the easiest row or column, it's one that has zeros in it. So pick a row or a column that has zeros in it is usually a good strategy. I'm gonna pick, maybe I'll pick this row here because it has a 0 in it. If you wanted to do like that column, it would probably be just as easy. I don't know. I like that row. So I'm gonna go with that row. What you're gonna do is you're going through each, so in this row, you're going through each entry Again, you just have to pick one row or one column, right? So you just have to do this like in total 3 times. 1, 2, 3, right? However you work it, right? If you're picking like this column, for example, you do 1, 2, 3, right? I'm doing this middle row. What you're going to do is you're going to do 0, so the number that you're looking at, 0 in this case, times -1. It's always -1. It's to the power of the place that that 0 is in, right? So if this matrix is 1, 2, 3 by 1, 2, 3, this 0 is in 1, 2. So it's -1 to the power of 1 plus 2. You see how I did that? Good? Show of hands, who's with me? Okay, good. Then take a pencil or whatever. And so if we're looking at this one, we're going to cross through everything in that column and everything in that row. So we were looking at 0, we crossed through everything in both of those columns and rows. Whatever's left over, so we're left over with 2, 1, 4, and -2. Those are the things that have not been crossed through. You take the determinant of what's left over. 2, 1, 4, -2. So we've turned the problem from a 3 by 3 determinant into a 2 by 2 determinant. So you could, if this was like a 5 by 5, you could break it down into 4 by 4s using cofactor, and then break it down into 3 by 3s. So you could see how this would be a long process, right? But anyways, then you move on to the next one. So now we'll do, I'll erase this as best I can. Sure. So now we're looking at like the middle one, the 3. So I'm going to draw, again, lines through it. So we're going to add. It'll be 3 times -1 to the power of 2 plus 2, right? Times the determinant of what's left over. So it's 7, 1, -3, -2. Make sense? And the last one, if I erase some of this, I know I'm leaving random lines places, but I don't remember what those numbers were. Is it 2, 4? I think so. I better double check. Yeah, it's 2, 4. Draw a line through the last one. So it's -1. It's in position 2, 3. So we're going to do times -1 to the 2 plus 3. And then determinant of what's left over, 7, 2, -3, 4. So that's it. Now, the idea is hopefully the determinants that you got there are easier to do, which in this case they are because they're all 2 by 2s. So this one is 0 times something, so this whole thing doesn't matter, right? That's why the zeros are nice. You don't have to do any work for them. You can actually just skip them on an exam. You don't even have to write them out. This is 3, -1 to the power of 2 plus 2 is, so -1 to the 2 plus 2 is -1 to the 4. If it's an even power, it's always going to be 1. You can type it in your calculator if you don't remember, but so this is just going to be +1 times this determinant, and then minus, so it'll be -1. This is going to be -1 to the 5, so it'll be -1. -1 times -1 is +1. And then the determinant here. Doing these determinants using the trick. So 7 times -2 is -14. Plus 3 is 11. Times 3 is 33. And then this one, 7 times 4 is 28. Plus 6 is 34. Hopefully I did that right. There's a good chance I didn't. But 67 if I did the math right. Sorry, I should just Is it negative 33? Yeah, you're right. Did the math wrong. Thank you. So it should be the negative 1. Positive 1. Yep. Thank you. Did I make any more mistakes? It's very likely. All right. I'll say that I got that right and hope. Yeah. Okay. Sounds good. Maybe this is a good sort of segue. So I'm going to stop my recording here.